Okay, folks, today we are going to learn about growth and decay. There are many examples of growth and decay in the real world that occur at a constant percent rate. These phenomena give rise to exponential functions. These functions will be easy to build and understand if we are comfortable with percent growth or percent increase, or percent decay or percent decrease. Think about every time you have to find a percent of something or a percentage of something. The operation that we use is multiplication. And since exponential functions are multiplicative, that is why anytime something grows or decays by a constant percent rate, we will be creating an exponential function. In this lesson, we would like to develop and understand methods for increasing and decreasing a number by a certain percent. We will start with the increasing case. A population of fruit flies is growing at a constant rate of 6% per hour. Population starts at t equals 0 hours with 28 flies. Find the population of fruit flies an hour later by first finding 6% of 28 and adding it to its original population. So let's go back to what you learned about percents in middle school. If we wanted to figure out what 6% of something is, since we know percent is out of 100%, when we divide 6 by 100, we get that that's 0.06. So to figure out how many flies we'd have exactly 1 hour later, we would take the number we had originally, which is 28 flies, and then we would calculate what is 6%. In other words, we would say 0.06 times 28 flies. So if we use our calculator and we pop that in, 0.06 times 28 gives us 1.68. So we put this together and we get that this would be approximately 29.68, which it doesn't make sense to have 0.68 of a fly, so we'll just use rounding rules and we'll say that we have approximately 30 flies. All right, find the population of flies an hour later by a single multiplication. Why does this work? So if you go back to what you did in middle school, a lot of times you did a couple of steps. You figured out what 6% of the value was, and then you added it to the original value. What if we could do this in one step? When we look at this structure, both of these terms have 28 in common. So if we were to factor that 28 out right here, even though you don't realize it, it's really like having a 1 right here. So what we're left with is 1 plus 0.06. And if we put that together, that becomes 28 times 1.06. If you then type that in your calculator, it'll give you the exact same answer that we got the last time. It'll tell you that that is 29.68, which again, because this is flies, we're going to round and say that is 30 flies because we're not going to have part of a fly. So why does this work? Anytime we're doing percent increase, you want to keep 100% of what you had, plus add the percent that it's growing by. So we want to keep 100% of whatever it was we have, and we're going to add the 6% to it. So technically, when you put that together, you want 106%. When you then change that to a decimal, because you divide by 100, it moves that decimal 2 places to the left. So that makes that multiplier 1.06. The 1 holds the original amount there, the 28, and the 0.06 adds the percent growth to it. So instead of us having to do all these work and all these steps, we can do this with a single multiplication. Okay, so let's put this together. It says determine the population after each of the following amounts of time. Show the calculation you use as a repeated multiplication. So regardless, we start out with 28. Think about this. When we had 0 hours, the population is 28 flies. So after 1 hour, we would have 28 times 1.06. After 2 hours, what happens is we would take this amount that we have right here, and I'm not going to worry about rounding them yet. I'm just going to put them like this to 2 decimal places. We would take this 29.68, and then we would multiply it by 1.06 again, because each hour it gains another 6% of what it had the hour before. So again, the 1 would keep that there, and then the 0.06 would add to it. Well, if I multiply this number right here, this 29.68 by 1.06 again, really what I'm doing is I'm saying 28 times 1.06 to the second power. because I've now multiplied by it twice. And then if we go over to 3 hours, we would multiply by 1.06 again. So this would ultimately be 28 times 1.06 to the third power. Now, obviously, because this is about flies, we would not say we have 29.68 flies or 31.46 flies. So we'll go ahead and round that off. This one, we'll just use rounding rules here. That would be that we had around 30 flies. This one we'd say we had around 31 flies. And then this one we'd say we had around 33 flies. Now, because we've only done this a few times, it might not seem like it's growing that fast. But if you continued it and went to like, what if it had been 10 hours or 20 hours or 30 hours, you would see these numbers increase quite a bit. It would not seem as linear as it does right now, because when, like all exponential functions do, once they take off, they really take off. All right, so this next part, find a formula. I don't know what that is, sorry y'all. That models the population P as a function of time in hours T. All right, well, if we look at this, just like we've learned about all exponential functions, we have that basic form y equals a times b to the x, where a is our initial value and b is our multiplier. So in this case, we would say P of t, the population according to time, is equal to our initial value of 28 times our multiplier, which is 1.06, raised to the t. What is the value of P of 24? And what does this represent? Well, now if you were to substitute 24 into this function that we have just written, and we can do this by using our graphing calculator or by using Desmos. You can type this right on Desmos. So you can go in Desmos and type 28 times 1.06 raised to the 24th power. We would get that that is approximately 113 flies. So what does that mean? Well, what that means, folks, is 24 hours after this little experiment or study began, there are about 113 flies. Let's look at this in Desmos real quick. We could go into Desmos, type this function in, y equals 28 times 1.06 to the x, and do y'all see how it has that curve to it? It doesn't increase as fast as one that's doubling, but it's definitely that exponential function. Remember, when you're working with Desmos, you can always click in there, change this to a table, or you could have duplicated before you changed into a table. You can keep pressing enter, and at first, like I said, it might seem like it's kind of linear, but if you do it over time, you can really see how they get further and further and further apart. So if we get all the way down here to 24, we can see that at 24 hours, there's about 113 flies. Where if you continued going out, it really starts to take that exponential turn where it's growing faster and faster and faster. All right, let's look at the decreasing case now. Decreasing by a certain percent will follow a similar pattern to the increasing case. A cup of coffee is cooling down such that its temperature is decreasing at a constant rate of 8% per minute. Let's say the coffee starts at a temperature of 200 degrees Fahrenheit. Find its temperature after 1 minute by finding 8% of 200 and then subtracting. So going back to what we did back in middle school, so we would have said 200 minus 8% of 200. So we would have changed that to 0.08 times 200, because remember, you always take percent and divide it by 100 or move it the decimal 2 places to the left. So what happens is that's 200, and 8% of 200 is 16. So that would have ultimately given us that after 1 minute, the temperature of our coffee is 184 degrees Fahrenheit. Now it says find its temperature after 1 minute by finding a single product. How can you interpret this in terms of 8%? Okay, so here's what I want you to think about, folks. If the coffee is losing 8%, that means it is cooling by 8% each minute. So if that's happening, what is it keeping? That's what you have to think about. So if it's losing 8%, it is keeping 92%, because percent is always out of 100. So if we kind of do this whole thing like we did last time, where we think about, this being a binomial where both of them have that 200 in common, If we factor that 200 out, ultimately what happens is it leaves us with 1 minus 0.08. And so when you do that, that's really saying 200 times 0.92. And that makes sense. We're losing 8%, so we keep 92%. So therefore, our multiplier is 0.92. And this is called our decay factor. If you ever have a question that says, what is the growth factor or what is the decay factor? For our last problem we did, the growth factor was the 1.06. It's the same thing as your multiplier, where for this problem, that decay factor is 0.92. And if you pop that in your calculator, it would give you 184 degrees Fahrenheit, and we can do it all in one step. So what will the temperature of the coffee be after 2 minutes? Round to the nearest degree. Now that we realize if we're going to lose 8% every minute, we're going to keep 92% of what we had the previous minute. So all we have to do is say 200 times 0.92 raised to the second power, because if it's been 2 minutes, it's lost 8% twice. And if you pop that in your calculator, that is about 169 degrees Fahrenheit. So when decreasing by a certain percent, we need to think about what percent remains. All right, read this next problem. The enrollment of students at a school is decreasing at a constant rate of 5% per year. What percent remains after 1 year? Take a second and think about that. If they lose 5%, what percent do they keep? Hopefully y'all can all see that would be 95%. Again, because it always comes from 100%. 100% minus 5% would keep 95%. If the population this year is 2,300, what is its population the next year? Do this in a single calculation. So our initial value is that 2,300, and then we would multiply by 0.95, that decay factor. And since it's only in 1 year, you only do it one time, and that would give us 2,185 students the next year. So what would the population be in 5 years? Well, of course, I don't want to sit there and keep multiplying by 0.95 over and over and over again. So instead, I use our knowledge of exponential and functions. Our initial value is 2,300. Our multiplier is 0.95. And since it's 5 years, we will raise that to the 5th power. And when we pop that in our calculator, that is going to give us 1,779.7 students. But of course, we can't have a part of students, so we'll just use some rounding rules and round to the nearest student. So that would be 1,780 students at this school 5 years from where this study began. Okay, so let's put this all together. So our basic formula for any exponential function is y equals a times b to the x, where a is our initial value and b is our multiplier. Remember, anytime the multiplier is a number greater than 1, it grows. And anytime the multiplier is a number between 0 and 1, it decays. The formula we're going to use for percent growth and decay is pretty much the exact same thing. It's still y equals a times b to the x. The only difference is, to get the b, to get that base, which is our multiplier, if it is growing by a percent, we are going to do 1 plus the rate it's growing at. And when we do that rate, it's always in decimal form. So you're always going to take your percent and divide it by 100. Where if it's decaying to get that base, we're going to do 1 minus that rate. So think about what we did here. When it grew by 6%, we said 1 plus 0.06, which gave us our multiplier of 1.06. Where when it was decaying by 8%, we said 100% minus 8%, which was 92%, and our decay factor right here was 0.92. Some words you definitely want to make sure you look out for are things like growth, appreciates, increases. Or for decay, depreciates, or decreases. If you're not used to the words appreciate or depreciates, appreciate and depreciates are for things that grow or decrease in value. That's what that means. So we might say like a property appreciates over time, meaning it increases in value. Or when you buy a car, the car's value depreciates over time. So these are just keywords to look for. All right, so let's do a full-on problem. It says $5,000 is invested at a rate of 4%. Determine the amount after 5 years to the nearest cent. Okay, first of all, y'all, if we're investing money, we want it to growth. So this is a growth problem. So we'd say, okay, what is our initial value? Well, our initial value in this case is $5,000. Now we have to get our multiplier. Well, since it's growing by 4%, what we're going to do is we're going to take that percent and we're going to change it to a decimal. There's two ways to do this. One is you put the decimal down, move it 2 places to the left, so you get that that's 0.04. Or if you have a hard time changing percent to a decimal, just always make it out of 100. Pop it in your calculator and it'll give you 0.04. Remember, though, we need the 1 there to hold the amount we had. You can't just multiply by 0.04. You're going to lose a lot of money. So you're going to say 1.04. And then since it's been 5 years, we'll raise it to the 5th power. And guys, you can go right into Desmos, type this in, or if you have a graphing calculator at home, you can type it in. So we pop that in and we get that that would be $6,083.26. It's said to round to the nearest cent, so that's to the nearest hundredth, which is what we normally do with money. Make sure you always follow the directions. Again, if you're using Desmos, it's real easy, guys. You just type it in like you type in your home screen, and over here, it'll give you the answer. Or you can always write it as a function and make it into a table. All right, let's look at the next example. If the savings in a bank account can be modeled by the following function, which of the following is true? Well, first of all, I hope you notice by looking at this function, look at your multiplier here. It is 1.045. So this is definitely growing, not decaying. The initial value is always the part that is not being raised to the exponent. So this is our initial value right here. So when it says the initial amount deposited was $250, that is true. The B is incorrect because it says $2.50, and D is incorrect. They have those answer choices on there to trick you because of the moving of the decimal for the rate part. All right, then we have to look at this. If our base is equal to 1.045, then just the R part was 0.045. To change that back to a percentage, you do the opposite of what we did before. You would move that decimal now 2 places to the right instead of 2 places to the left. So that means that that would be 4.5%. Or you can always just change it back by multiplying back by 100. When we change from a percent to a decimal, we divide by 100. So to get it back, you would multiply by 100. So we can see that the correct answer here would be answer choice C. The initial amount was $250 and the interest rate is 4.5%. All right, let's look at a decreasing example. If a city with a population of 50,000, is decreasing, keyword here, at a rate of 1.16% each year, write a function P of t that models the city's population over t years. Okay, again, you got to be really careful and make sure, even though this has a decimal in it, folks, it's still a percent. You have to change it back to a decimal first. So we have that 1.16, and we're going to move that over 2 places to the left to get 0.0116. Then to get that base, because this one is depreciating, instead of saying 1 plus the rate, we're going to say 1 minus the rate. So we're going to say 1 minus 0.0116. And if you pop that in your calculator, that will give you 0.9884. So to write our function, we would say P of t is equal to 50,000 times 0.9884 raised to the t power. And that makes sense, guys. It's supposed to be decreasing, so this base right here shouldn't be a number greater than 1. It should be a number less than 1. Another way you can look at it is you can do it all in terms of percent to start out with. So you can say, okay, remember in the beginning, you initially have 100% of what we're working with. So we have 100%, and then we're going to lose 1.16%. So you could type that in your calculator, which would give you 98.84%. Then divide that by 100, because we got to change it to a decimal, which will give you that 0.9884. So some people like to change it to a decimal first, and then you either add it to 1 if it's growing or subtract it from 1 if it's decaying. Or you can always do it from percent. You can say 100% plus the percent, then change to a decimal, or 100% minus the percent, and then change to a decimal. All right, what will be its population after 10 years? After 50 years? So all we need to do is use Desmos, or for those of you who have a graphing calculator, use your graphing calculator, type this function in. I'm going to come right here if you're using Desmos, and I'm going to duplicate it. If you're using your graphing calculator, then just go to table. I want to find out what would the population be after 10 years. And I'm sure if this was a regular problem, that would tell you to round to the nearest whole number because you can't have part of a person. So the answer would have been 44,494 people. And then for 50 years, we would just go to 50 and see that's about 27,900 people. Okay, so folks, you're going to have a few Delta math problems to do. It's just like what we were doing. Look at this one right here. You have $7,700 is placed in an account with an annual interest of 8%. How much will be in the account after 22 years to the nearest percent? So what you would do is you would say 8 divided by 100%, which is 0.08. You would add that to 1, so the multiplier would be 1.08. And then you would go in your calculator, and you can actually use the calculator right here in Delta Math if you would like. And you would type this in. You would say 7700 times 1.08, close that parenthesis, raised to, and because it's been 22 years, we would say to the 22 power, press enter, and we would take our answer that it gives us over here. So we would say 41,861 point, and it says to the nearest cent. So use your rounding rules, 36. Submit your answer. And of course, in Delta Math, if you're doing something wrong, it's going to show you what you're doing wrong. It's going to try to explain it to you, show you how you get that exponential growth rate, how you write your function, and then you substitute in. So if you're getting something wrong, try to look over this and see what you're doing. Good luck. We're going to come back to this tomorrow and add on to it. You've only got 6 problems to do today. Talk to y'all tomorrow.